Hello, section 5.8, analyzing graphs of polynomial functions. And to start this section out, we're going to use this function to talk about the difference between four terms. These terms are zero, factor, solution, and x-intercept. So first, we're going to talk about the difference between a zero and a solution. A lot of times in the homework problems, we'll be asked to find zeros to a function and solutions to an equation, and you may not catch the subtle difference. This is a function. This over here that I'll write, this is what we call an equation. Now this is an equation too, sort of. It's got an equal sign, but it doesn't have something that it's equal to, a number that it's equal to. This does. This is telling you this for sure needs to be equal to zero. This doesn't have that specification. It could be equal to anything. You can put anything in for x. For instance, you could put in a 1, and if you put in a 1, you would get 12. If you put in 0, you'd get 6. And you could go on forever, putting whatever you want in for x and just figuring out what y would be. Here we're saying it has to be 0. Okay? So the solutions to this equation are set. There's just a set number of them. There are 2 of them in this particular case. Here, there's just any number of solutions that we might want to this equation, this function. A solution is just any x and y that make both sides of the equation equal to each other. And that's what we want. We want them to be equal. So the solutions that we are especially interested in are the ones that we call zeros, because when you put them into the function, you get 0. And if we were to figure that out, we'd say, well, let's first factor this. Right, this would be x plus 2 and x plus 3, and we'd set that equal to 0. And then we would say, well, x must be negative 2, or x could be negative 3. Both of those make us 0, right? Or if we were just plugging in numbers for x and we just happened along negative 2, we would get 0, and also negative 3 would give us a 0. So we say that negative 2 is a 0 of this function, right? Because this function could be equal to anything. We could put anything we want in for x, and whatever we get for y, we just write that down, and that's a solution. But negative 2 and negative 3 are particularly special solutions, ones that give us a 0 when we put them into the function. Over here, this guy is destined to be equal to 0, and it couldn't be equal to anything else. So just the solutions, there are only a certain number of solutions. There's 2 solutions. And we would just factor this, set it equal to 0, just like this, the same exact process, and find, again, negative 2 and negative 3, and we would say negative 2 is a solution because we started with an equation. So negative 2 and negative 3 are both solutions to this equation. Okay. Now we come along this term factor. Notice that we got the zeros, negative 2 and negative 3, and if we had done this problem, step by step, we would have factored it as well. They are closely related to the factors that gave us those answers, that gave us that 0 there, or would have given us these solutions over here. So if negative 2 is a factor, let's see. If negative 2 is a factor, then x plus 2, I have mistakenly said factor when I meant to say something else. If negative 2 is a 0, then x plus 2 is a factor. Okay. It's going to be a factor of this function, of this polynomial. If negative 3 is a 0, then x plus 3 is a factor. Okay. And that works for any 0. If k is a 0, Then, and notice that if it's negative 2, you get x plus 2. Negative 3, you get x plus 3. So it's the opposite. So it'd be x minus k is a factor. Okay. The last thing is an x-intercept. Okay. An x-intercept is on a graph, and we graph functions. Okay, you can't really graph an equation. It just is a couple of numbers. A function, though, can be, like I said, any set of x and y that make both sides equal. And since there's so many of them, we use a graph to represent them in a picture. So, we have a few solutions here. 1, 12. Let's say that is 1, 12. Then 0, 6. So it would be about halfway up there. Negative 2 and 0. So that's 1. So negative 2 would be something like right there. And negative 3, 0 would be about there. Right? And we could keep plotting all of these solutions. We could go in between 0 and 1 and put a point somewhere in here. We keep putting points in here and down here. And as we put down all those points, all the infinitely many points that we could put down in here, what we would start to get is a shape like this. In this case, at least. Not in every case. This one looks this way. Oh man, that's awful. But there you go. Okay. It's possibly the worst graph ever, but there it is. Right, and this, you can think of this as just tons and tons and tons, infinitely many little points that we've put on this graph, on these axes to show all the solutions to this function. And what we see here, let's see, right here and right here are the places where the graph intercepts the x-axis. Those are called the x-intercepts. X-intercept, x-intercept, and where do we see the x-intercepts? Where the zeros are. Okay, so a function has zeros. These numbers, these zeros, are the same as the solutions to this equation where you have the same polynomial expression set equal to 0. These numbers are where you will find x-intercepts when you draw the graph. And when you have these numbers, these zeros, then you can conclude that x minus that 0 is a factor. Right? X with the opposite of that 0 is a factor. So that's the connection between all four of those. We have zeros and solutions and factors and x-intercepts. All right. One more thing that I want to highlight in this video is what the book calls turning points. This color. So if we had some graph and it was like this, these right here, this guy, or this way down here, this up here, this down here, the book calls these turning points. So you want to know that vocabulary that they're using. I think it's kind of silly because what these are really called are maxima, or extrema, excuse me. Extrema. Okay. Because in their localized area, right here, not overall the whole graph, but just right in here or right in here, in their little neck of the woods, they are the extreme high, the extreme low, extreme high, extreme low. This is called a maximum. This is called a minimum. And again, we're back to a maximum and a minimum. Okay, so if you're at a maximum or a minimum, both of those are examples of extrema. This is an extreme. This is also another extreme. This is extreme, the most extreme high and the extreme low in their little area, localized. Okay, so turning points, extrema, they're the same thing. The point here is, let's ask ourselves, what degree might this, if this is a graph of a polynomial, what degree might this be? Take a look at, let's not phrase it that way. This could possibly be, if we have 4 extrema, then this could be, since we have 4 extrema, or turning points, this could be degree 5. And that would be at the least. It'd be at least a degree 5. Let's go the other way. Let's say we had a degree 3. Let's say we had a degree 3. How many turning points could that possibly have? Well, let's think about how many solutions a degree 3 would have. It would have 3 solutions. And let's draw the graph so that we just talked about the connection between solutions and zeros and x-intercepts. So how many zeros could this degree 3 have? It could have 3. So let's draw a graph, just a made-up graph that has 3 x-intercepts. So it has 1. We got to come back down so we can have a second one, and come back up so we can have a third one. We could do it a different way. We could start up here, come down and have a 0, have another 0, and a third 0. Any way we do it, we're going to wind up having 1, 2 extrema, 1, 2 turning points. So a degree 3 is going to have 2 turning points. Or let's just say extrema, because we want to sound like mathematicians. 2 extrema. Let's say we had a degree 4. We're going to have 4 zeros, and let's draw a function that has 4 zeros, 4 x-intercepts. There's 1, 2, 3, 4. So we've put in as many turning points as we possibly could, so we have 3 turning points, 3 extrema. Extrema. Okay, so for a polynomial, I'm going to shorten that, polynomial, of degree n, the graph has, at most, could have less, but at most it has n minus 1. 1 less than the degree. 1 less than the degree. 1 less. 1 less. Has at most n minus 1. We're going to say extrema, even though if you read this in the book it says turning points. And that is just a useful thing to have in your mind, to know that that's the case. When you look at it, you know, oh, looks like it's got to be at least a degree, whatever, at least a degree 5. It's got to be at least a degree 4, degree 3. So that's just what I intended to be a quick little add-on. Went a little bit longer than I thought, but that is a useful piece of information just to have logged in your head. Okay, so we'll do some specific examples in the next video. Thanks for watching.